Hello, everyone. Welcome to DFI's Impact webinar. For our new attendees, DFI's Driven Pile Committee hosts this webinar to highlight innovative developments, current practices, and case studies focused on driven pile foundations as it relates to this month's webinar, driven by any means, not necessarily just impact hammers. And if there's anything pile related that can benefit the industry, we would like to help get that information out. So if you have any topic suggestions or would like to present yourself, please reach out to a committee member. And to introduce myself, as you can see, my name is Travis Coleman, work for GRL Engineers, and I am in our Chicago office. Very quick housekeeping. So you will be muted, you are muted during the webinar. If you have any questions, please use the chat function and I'll monitor those questions and I will bring those to our presenter as they close out. So our presenter today is someone that most of you are very familiar with, Gerald Verbeek of Allnamics. Gerald's quite active in DFI and speaks frequently and enthusiastically about some topics, including CPT soil sampling and today's topic, vibratory hammers and their related modeling and monitoring. And with that, Gerald, it's yours.
Thanks, Travis. I appreciate the invitation to talk, and I appreciate the opportunity to really talk about a subject that is very near and dear to my heart, and it is vibratory pile driving. And what I would like to do today is talk a little bit about vibratory driving in general, but with a special focus on signal matching. Most of you know signal matching from driving a pile with an impact hammer. That's something that we've been doing for a long time, since the 1970s, whether it is with CapWeb software or with an alternative of that. But when it comes to vibratory driving, signal matching is kind of unknown, barely used, and hopefully I can present to you today what the options are and see what we can do there. What I would like to do in this webinar is to demonstrate that vibratory driving can be approached in exactly the same way that all of us are used to when it comes to pile driving with an impact hammer. You do a simulation, you do your monitoring, and then you do your data analysis, your signal matching, whatever you want to call it, your restrike that you normally do with an impact hammer. You can do exactly the same thing with vibratory driving. But it means, realistically, that we really need to make a concentrated effort within our industry to start doing monitoring during vibratory driving. Because as I will point out a little bit later in the webinar, that is something that is not commonly done. Most of the time when you talk about vibratory driving, you'll get a story, well, we were able to drive it to a certain penetration. Sometimes a little bit more detailed, like, well, it was fairly easy, or well, it took quite a bit of effort, but that's about the extent of vibratory driving monitoring. And what I hope to achieve with this webinar is to encourage all of you that use vibratory driving to start using monitoring on a routine basis. And then finally, to figure out or to explain, to clarify how you can utilize that monitoring data to analyze that data, just like we're used to with impact driving, with signal matching, to come up with capacity figures. Why is it that we trust high-strain dynamic testing and the analysis of that data through signal matching to come up with the capacity or for a pile that was driven with an impact hammer, and why not with a vibratory hammer? It's all the same process, and hopefully I can expand on that. So let's talk a little bit about introduction. What you see here in the previous picture, and again this picture, large diameter piles. And those large diameter piles need to be driven into the ground. And quite often, the vibratory process is faster. But not only that, the piles are getting larger and larger, so that you really need to start thinking about, is it realistic that I can still do this with an impact hammer? We also have plenty of sheet piles. And with sheet piles, it is almost a no-brainer. We drive those with an impact hammer or with a vibratory hammer. So the question then is, well, if we can do this and feel comfortable to do this with a sheet pile, why not with any other type of pile? And why can we drive a steel sheet pile into the ground with a vibratory hammer and nobody's asking any questions about it? And why would we have some reluctance to do it with an open pipe pile, for instance, where people are saying, well, maybe we still need to use an impact hammer, especially for the final part of the driving process. True enough, when you have a sheet pile, you generally are not that concerned about the bearing capacity of that pile. But hopefully, as I pointed out earlier, I can show you that we can do the same thing when you drive a load-bearing pile with a vibratory hammer. I already told you that things are getting bigger. What you see here is a picture a couple of years ago of a vibratory hammer, or two in series actually, and you see Peter Middendorp, the president of Allnamics, standing next to it. Things are definitely getting bigger. Here's another example. This was for an offshore job where you see a pile about 42 meters long. You see the people there in the orange suits at the bottom, center of the picture, and you see the size of the vibratory hammer. Vibratory hammers are getting bigger and bigger and allow you to drive larger and larger diameter piles. Sometimes, though, it goes even a little bit more than that, and this is where I really got excited about vibratory driving. A long time ago, a couple decades ago, somebody in Hong Kong was thinking about putting a bridge together between Hong Kong and Macau. The reason for that is simple. If you are driving at that time, before the bridge was there, from Hong Kong to Macau, you had to go all the way around the delta, and that took you hours and hours. And it would be so nice if you had a bridge that would just take you a little over an hour to go from one place to the other. So the idea was there, and then it's easy to put the idea in a drawing, as you see on the right-hand side, where you basically say, well, a bridge all the way is a problem, because then the ships that go into Hong Kong harbor, there's a height limitation there, or you need to open the bridge. So why not do it simple? We just have a bridge on either end, and then in the middle we have a tunnel. Obviously, you need to transition between the bridge and the tunnel, and then we just put some artificial islands in there, and we just draw some trees on this whole thing, and that's simple. The drawing, very simple indeed. No major problems to draw that. In reality, though, a little bit harder. But when the design got developed a little bit in more detail, people said, okay, that island, maybe we need to orient it slightly differently. Here you see that the island was kind of perpendicular. The longest axis of the island was perpendicular to where the bridge and the tunnel would go. In reality, it was more parallel. And by the way, we can make this island, no problems. We're just going to drive 61 or 62 open steel piles. We put it on the edge of the island. Then we put some steel to those piles to make them more watertight. We pump the water out, fill it with sand, and hey guys, there we are. Piece of cake. I know, by the way, the steel piles are 72 feet in diameter. And that is when we first started thinking about, okay, what are the limitations of vibratory driving? Because this is one of those piles. And again, you see there the people on the bottom in the orange suits. The people are getting smaller and smaller, or the piles getting larger and larger, whatever it is. And we came up with a problem where we had a 72 foot diameter pile, about 180 feet long, weighing some 660 US tons. And we had to drive those piles 25 meters into the seabed, or a little over 80 feet. Not that hard driving. The end values were between 8 and 40, so no real strenuous driving. But still, how do you drive something that is that diameter into the soil? And then the other problem that we came into, started to realize, is that when you have a pile that is 72 feet, what one side of the pile sees and what the other side sees is not necessarily the same thing. But we started looking at our design methodologies and started thinking, okay, what should we be doing here? And we said, okay, fine, let's just do pile driving simulations. Yeah, just what you're doing when you have a pile with an impact hammer. You plan your pile driving process. When we do it for an impact hammer, we figure out what the stresses are, both tension and compression. You select your hammer. You figure out how deep it can go into the soil, and you predict your bearing capacity. Now, of course, in this case, the bearing capacity was not the biggest concern, but if you say, okay, we can follow exactly the same approach again for the vibratory driving, and we did that, and we, on that basis, were able to figure out what kind of hammer we had to use. And as you can see here, all the piles were driven within a matter of minutes into the soil. We then filled them with sand, and that was the outline of the artificial island. But that project alone really got me all hooked and hyped about vibratory driving, because that is really, if we can do something like this, we can basically tackle most other jobs. Here you see another indication, and it also shows you one fundamental difference between impact driving and vibratory driving. When you have a pile that's being driven with an impact hammer, you have the pile sitting partially in the soil, and you have the hammer sitting on top of the pile. But that's it. Whenever the hammer is creating a blow onto your pile, that force is really determining, together with the soil resistance, what the set of the pile is going to be. The vibratory driving system, it's different, because you see that the pile is hanging in the winch, and that winch is really holding the pile back. So when we are thinking about vibratory driving, it's a little bit more complex than pile driving with an impact hammer, because other than the soil, the pile, and the hammer, the three elements that you need to model, you also need to model the hook load and keep control of that. And again, we'll come to that in a little bit later. That is that hook load that is absolutely essential. So, first step then, pile driving prediction. With the software, and what you see here is nothing new. You see that we have the soil, we have the pile, and then the vibratory hammer sitting on top of the whole thing. And we can model that just like we do that with a pile that is driven with an impact hammer. We have the standard soil model, a combination of a mass, a spring, and a damper. We put the vibratory hammer on top of this whole thing that is creating some kind of sine movement to drive that pile into the ground. And then we use the method of characteristics to figure out how this is going to go. This is, by the way, a very important thing when you do, at least in my opinion, when you do pile driving simulations, use the same algorithm, the same method to calculate the outcome of that simulation as you would use later on with your pile driving analysis. If you use the method of characteristics, you can use it throughout, and that means that you can utilize the data, the outcome that you have from your signal matching or from your analysis, can utilize it again into other simulations, and that is very advantageous. Now, when we do that modeling, again, there are a couple of minor differences there compared to impact driving. Well, first that you see there is on the left-hand side, you see there the combination of the spring and the dashpot. The dashpot dealing with the damper to describe the effects when it comes to the velocity. And most of the time we have some kind of exponential relationship between the two. And the springs, most of the time we're using a elastoplastic soil model, where you basically assume that it first goes, the first part is elastic, that you see over there, the first part, and then suddenly it goes over into a straight line where you have the plastic behavior of the soil. Not very realistic, come to that in a second, but that is the standard model that we're using. And then, of course, again, a major difference between impact driving and vibratory driving. With impact driving, you may have 100, 200, 1,000, maybe 2,000 blows, but that's about it. With vibratory driving, you're using that at a frequency of, say, 20 hertz. So there are 20 cycles per second, which means that within a minute, you're going to have 60 times 20. So you're already talking about something like 1,200 cycles in there. So in no time, you have thousands and thousands of cycles, which means that the soil fatigue that you have to address to some extent with impact driving automatically becomes a fact of life and something that you can simplify. And it was something that done many, many years ago, where you basically see that we're taking the strength of the soil by a certain factor, depending on what kind of soil you have, and you can more or less assume that reduction in strength does not take place over time as you drive the pile into the ground, but really takes place from the very beginning as you are driving the pile into the ground, because within a couple of minutes you have so many cycles that fatigue has all occurred. Now, I already talked about that elastoplastic soil model, still widely used, commonly used, and back many, many years ago in the late 80s, early 90s, George Goebel indicated that you should use this model, could use it very effectively for driving with an impact hammer, but it's not realistic. Soil doesn't behave that way. And so I think over time, and maybe we're really way overdue, we should start using the hyperbolic soil model, but that is for a later date and maybe another thing that we can talk about at some point in the future. So for now, this is the model that we're using. This is what we have, the elastoplastic and then the exponential damping element in there. And then you put in your data that you have on your pile, nothing special, the standard stuff that you get from there. And then you get all kinds of outcomes, just like what you would do with the simulations with pile driving with an impact hammer. You also get graphical things in there. And one of the most important elements in there is your penetration, which is basically in millimeters per second or inches per second, whatever unit you would like to use. How deep is the pile going, or how fast is the pile going into the ground as a function of depth? What you see on the vertical axis is the depth. The horizontal axis, you see your penetration speed. And at some point, obviously, you're going to have a refusal where the vibratory hammer is not able to make the pile go any deeper. And obviously what you want to achieve is that you size your hammer in such a way that you get refusal at a greater depth than your target depth. And in a way, it's the same thing that you do with an impact hammer. You select your pile in such a way that your blow count stays less than the refusal blow count, so that you can get your pile to the depth where you want to go. Very much the same. Use the same type of methodology, same type of approach to come up with your predictions for your vibro driving. And that is then what we call the learning loop. And when well before I got involved with DFI, or here even in the United States with pile driving, I was taught when I started my career with Shell, that you have to always think about PDCA, and it doesn't refer to the Pile Driving Contractors Association, but it's plan, do, check, and act. You plan your work, then you do your work, then you check or you analyze what the results are, and then you act accordingly so that next time you can do it better. You adjust your plan. It doesn't make any sense. It's not right that your plan stays fixed and firm. There's always room for improvement, and there's always room to do things better, differently, more efficiently, and that's what this PDCA is all about. Well, within Allnamics, we change it a little bit. We call it the Allnamics Learning Loop, but it's really nothing other than PDCA, but there's an additional step in there. And that is that red box that you see in there, where you now have your database experience. Basically, what you do is your plan is the prediction. Then you do it, and while you're doing it, you monitor your pile. Then you analyze those results. And you also do a post-analysis. You compare what you had before, your assumptions before, and what your assumptions are based on the analysis data, whether they're valid or whether they need to be adjusted. And then you stick that into your database, because that gathers the experience. And that is the point that we have to deal with when we talk about vibratory driving. Because as I told you, we can, when we have pile driving with an impact hammer, we've done this for a very long time. We've done this since the 1970s or so close to 50 years. And we basically look at all this stuff, and what you see here on the screen, control of the process, looking at pile integrity, because we can again define from the results that we're getting some information about integrity. We can do troubleshooting, all kinds of stuff. That's nothing new. But with vibratory driving, it's kind of like, we don't do that. When you ask somebody, well, what kind of monitoring did you do? It was kind of like, well, you mean whether we were able to drive the pile into the soil, to the target depth? Well, yeah, exactly. What kind of measurements did you take there? And it's kind of like, well, we didn't use an impact hammer, so we did not do any monitoring. But trust me, when we were able to drive the pile to the right depth, and everything went fine. But with that attitude, we don't learn anything. And one of the things that the Driven Pile Committee has been working on is trying to collect data so that people with vibratory driving can enter the data, so that we can analyze it better, so that we have a better database, so that we figure out how everything works with a vibratory hammer. Because that learning loop is essential. And that means that we need to fill the database, or experience base, with data that we have from vibratory driving. Why is it important? Well, I'll be very honest with you. When you are doing right now a loop like that with an impact hammer, we have so much experience that the safety margin that we have to build in sizing, for instance, our hammer, or the prediction how deep I can go, can be relatively tight, because we have so much experience that we feel fairly comfortable that we can make the right prediction. But when, on the other hand, we're dealing with the pile driving with a vibratory hammer, we have to be a little bit more conservative. So that means that you may say, like what you saw earlier when we had this huge 72-foot pile where we put 8 hammers in parallel, maybe if we had plenty of experience, we probably could have sufficed with 6 or even 5 or something like that. Nonetheless, we went with 8, just to play it a little bit safer. And we need to fill the database so that we can get that information. And on top of that, every method, even still with impact driving, we can still learn more about it. Maybe different soils, different ways of dealing with things. And that's, we need to get the learning loop in there. And we need to gain that experience. But just getting the monitoring data by themselves is not enough either. We need to also then take the analysis, the back analysis, to figure out what is happening so that we can really fill that database. And that means that we need to make not only predictions, which is the planning part, but also postdictions. I'll figure out, with the information that we now have, with the soil model that you come up with your signal matching, try to figure out what is really happening, what would have been happening, would you have had a different prediction, would that prediction have been more accurately reflecting the situation. And that's something where hopefully we are, as an industry, getting more and more honest about. We need to learn from the differences. We need to have the guts to make a presentation where we say, this is what we predicted, and it didn't work out that way. And what is the advantage from that? Well, then we'll learn from the differences. And one of the case studies that I'll be describing a little bit later on is doing exactly that. Because we need to fill that library. Now, This is an outdated picture of a library. Most of the people, when I would show this to my son, he probably thinks, Dad, come on, you don't need books anymore. Just give me a whole bunch of files. And when he went to OU about 8 years ago or so, everything was electronic. But when it's electronic or in real life, on the left-hand side, we have the library where we have more than 50 years of experience. On the right-hand side, the library for vibratory driving. It's filling up fast because people are getting more and more interested about, but there's still an awful lot of open spaces, and we really need to see how we can fill that and get more information on that. So we've done the prediction. I showed you how that works. Basically the same thing that you're doing normally. And then it comes, okay, how do we go from here during the monitoring? And again, it's very familiar. You basically have a strain and accelerometer, or a strain gauge and accelerometer, sensors for the strain and accelerations, just what you used to with monitoring during impact driving. You need to send the data. Most of the time we put something on the pile that has a wireless connection to a laptop where you get all your data. And then we need to analyze the data, just what you would do with PDA, and we call it in VDA, a vibratory driving analysis. But it's pile driving analysis. Exactly the same thing that you normally do. This is how it looks. And again, something that is probably nothing new for you guys. You've seen this time and time again. The only thing that may be slightly different for some of you is that you're used to having your accelerometer and your strain gauge side by side. We put it on top of each other as a combined sensor, but yeah, it's exactly the same situation there. And then we start doing monitoring. And with the monitoring, we do exactly the same thing that you do with your pile driving with an impact hammer, but there are a couple things that are different in there. You see that we are monitoring the frequencies as well. You need to figure out what the frequency is of the vibratory hammer, because if that changes, as we're going to see in a little bit, that may have an impact on how you drive your pile into the ground. If we look at the stresses, both tension and compression, we'll look at the hammer performance, we'll look at the troubleshooting, and then you also see that we have a fatigue analysis. Again, a misnomer. But especially when we are using vibratory driving, a lot of that has to do with offshore pile driving. And in the offshore world, steel fatigue within the steel piles is a very important issue. And what people are worried about is what I mentioned earlier about the fatigue in the soil. And when you have a pile that's being driven with an impact hammer, you may have maybe a couple thousand blows, but that's about it. But in vibratory driving, you have already 1,000 cycles within a minute. And it means that your total number of cycles is much, much higher, because it's not unusual that it takes about 25 minutes to drive a pile to penetration depth. So you talk about 25, 30,000 cycles. That scares structural engineers, because they're saying, oh, with fatigue, you cannot do that. Now, the nice thing is, since the stress levels with vibratory driving are a lot lower than with impact driving, and if in the end, it's really not a major issue. Most of the time, the fatigue aspect of pile driving with the vibratory hammer is even less severe than with an impact hammer, but it's something that you need to look at, and most of the time, people don't think about it when they're using it with an impact hammer, but with a vibratory hammer, it's often asked for, and you need to look at this whole thing. And then hammer performance and troubleshooting. Yeah, exactly the same thing. And again, I cannot overemphasize the value of monitoring. Yeah, and again, comes back to plan, do, check, and act. Monitoring to me should be applied every single time that you drive a pile. Because once you drive a pile, you cannot look into the ground. You don't know what's happening below, and only if you take the measurements, you can figure out if something goes wrong, what's happening. And what I see, unfortunately, way too often is that something does go wrong. You have a whole bunch of people standing around the pile, looking down, trying to figure out what's happening below grade. We don't have a clue. And then we start to talk, well, maybe this, maybe that, but we don't know. And at least if you have monitoring data, then you have a much better chance of figuring out what the problem is, and you save in the long term a heck of a lot of money. So you go back. This is your original prediction that we did on a pile, and the numbers are not that important, but you basically see again your penetration speed, and then here you see the depth where the pile is going, and you see that it's kind of between say 12 and 14 meters. We have kind of a difficult part where your penetration speed goes way down, then it goes back up again, and finally we go back down, and it's kind of stops, and at some point you hit refusal. Obviously, it's important that you keep this in mind and that you agree with somebody to figure out what's happening, because don't forget, this is in millimeters per second. So it's this is about 1/25 of an inch. So it's a very slow process. If you are going here between 0 and half a millimeter per second, it may be that is well within the accuracy of the prediction. And it comes back, as I said earlier, most of the time we try to be overly conservative, but sometimes you are not necessarily that conservative, but you need to think about it. So then we start doing our monitoring, and we figure out what's happening there. And you see here a pile with some data going into the ground, not necessarily the same pile. And I apologize for that phone call that came in. It was the answering machine. But here you see some monitoring data from another pile. And we're just going to look at the three different graphs that you see there. On the first one that is there is what I see here as well, where you have your on the vertical axis your penetration depth, and on the horizontal axis the maximum force that you put on your pile. And basically we see in here that the pile went down to about 20 meters, but that is where it stopped. And in reality, we thought we could go way deeper than that. So it was kind of like, well, it stopped. Well, when you then start asking questions, it was kind of like, well, yeah, we stopped at the 20 meters. It was kind of hard. It was kind of difficult to drive. And we don't think that we would have reached the final penetration. Besides that, for that project, you had to use an impact hammer anyhow at the end to drive the final part, so they just stopped it. And that's the risk that you have quite often, that people make decisions and don't necessarily get you all the data. But clearly, we could not go as deep as what we thought we could. So then we look at the penetration speed and start to figure out what's happening. And what's happening there is kind of weird, because initially, in this top layer here, you see that we would go down and back up again quite a bit. What is happening here? Well, it brings me back to what I said earlier. The penetration speed is not really the same thing that you have when you drive a pile with an impact hammer, because now I'm also dependent on how much hook load I have, the load, the uplift load that I have in my winch. And initially, quite often when you have a huge pile hanging there, crane operators are somewhat concerned. And they're basically saying, well, let's just play it safe. And they really hold it back quite a bit. And that sometimes is a problem, because if you don't give that pile that momentum, it's hard, it reaches refusal much easier. So here, these numbers are probably not as realistic. There it went up, but again, you see here that it went down by about 20 meters. It just came close to refusal. So what is going on there? Because again, that is not what was originally predicted. Well, then you're going to have something that is very telling, and that has to do with the power output. I will go back to the maximum force on the horizontal axis and the pile driving depth on the bottom. And you see that if you are around 15 meters or so, you have a maximum force of about 2.5 to 2.7 meganewton. Forget about the units. Units are not important right now. It's more the principle. Closer to 20 meters, where people said, hey, it's kind of getting tough to do this whole thing. We had a situation that you have a force there of about 2.1 meganewton. So if you look at this whole thing, you are losing about 20% from 2.5 to 2. You've lost about 20% of your force. You're going down, as it said, the power output dropped to about 80%. And this is where the frequency comes in again. Because when we went back to figure out what the frequency was that the pile was operating at, going from the now I'm losing from the top green arrow to the bottom green arrow. When we looked at the frequencies there, what you see suddenly is that the frequency dropped by about 10%. We went down from 30 hertz to about 27 hertz. You say, well, that's only 10%. Yeah, but the relationship between the frequency and the force is squared. So you go down from 0.9, from 1 to 0.9, or with your force, 1 squared is 1, 0.9 squared is 0.81, and that's where the 80% came from. So the frequency is extremely important that you look at it, but it also points something else out, where the big difference between pile driving within a vibratory hammer and impact hammer. With an impact hammer, you have individual blows, and those blows have a distinct starting point and a distinct end point, and there's a pause in between. Vibratory driving is a continuous process, and that's something that we need to look at a little bit later when it comes to signal matching, how you do that slightly different. Let's look at the signal matching, because now we have the data collected. We have some kind of rough indication why we have a problem. We recognize that because the frequency went down, we did not have as much force, and it may have caused the fact that the pile could only be driven to about 20 meters and not to the depth that we originally were looking for. So then you have signal matching. And what you see with signal matching there is kind of the standard thing. For those of you that are not that familiar with it, you basically measure your acceleration and your strain. From that, you derive your velocity and your force. You look at how those waves travel through the soil. You model the same thing again, and you use the measured force to figure out what kind of blow you have to measure in your software, and you come up with a measured signal and a calculated signal, and you compare the two. And as long as you have a good match, then you say, okay, now I know that my soil model is correct, because you assume that your blow, since it's measured, you know what kind of hammer blow you give. You also assume that your model for your pile is accurate, which if the pile is not cast in situ, most of the time that's the case. So the really only variable that you have is your soil model. And if you have a good match between the measured and the calculated values, you say, okay, now I know what my soil model is, and then you can use your geotechnical knowledge to figure out what your load displacement curve would be, what the capacity of the pile is. If on the other hand, your match is not that good, then you update your soil model again, and you do the same thing again. You run your software again, and until you get a good match. Nothing different, and this is where you see the same thing again. Now only with the measurements are done with your sensors, your simulation is done with your computer program, and there you go. As I said, very common for dynamic testing. Since the 1970s, early 1970s, this is being done time and time again. We do PDA during the analysis, during the pile driving, to get a rough indication of what the capacity is, with simplified equations, and then you do your high strain dynamic testing, or what is commonly known as dynamic load testing, to analyze your data. And then the question is, well, if this is commonly done for impact driving, why can we not do this for vibratory driving? Or maybe more basically, can we apply this technique to vibratory driving? First thing, of course, is that you have a completely different scenario between impact driving and vibratory driving. I already mentioned it a few minutes ago. With a impact driving, you have a clear start and a clear end of a blow. And therefore, you can look at each blow in isolation. and then try to do a signal match where you see the two lines in different colors, where you try to get the calculated and the measured signal to overlap each other as much as possible so that you get an indication of what your soil model is. Vibratory driving, as you see on the right-hand side, doesn't have that. It doesn't have a beginning and it doesn't have an end. And really, when you're looking at signal matching with vibratory driving, it's really the amplitude matching. You want to make sure that the amplitudes that you are getting, and of course with the right frequency, but especially the amplitude, that matches what you have with your measured signals. Because if the amplitudes of your measured signals match the amplitude of your calculated signals, then you have a correct soil model. So you can do this whole thing, but you need to look at amplitudes, and that quite often people are still talking about vibratory amplitude matching, which is basically the equivalent of signal matching, or what is here in this country often referred to as CapWeb, using the name of the software that's often used. So what do? Exactly the same thing as before. We measure with the strain gauge and the accelerometer, measure the amplitudes, we calculate with the software, and here you see the vibratory amplitude monitoring or matching. You calculate the signals, and if there's a good match, then we're okay. If not, we need to update the soil models. And if you have a good model, then you can figure out what your bearing capacity is and what your static load displacement curve is. One quick comment on that. Quite often I show here the picture of the same strain gauge and accelerometer. The strain gauge, generally speaking, is no problem. You can generally use the same strain gauge you can use for impact driving. Your accelerometer is slightly different because the frequencies are so much higher. Therefore, the forces on that accelerometer are a little bit higher. You may have to use a different accelerometer, but the principle is exactly the same. Now, let's put a case study together to show you how all this stuff works. At the end of this presentation, to show you how we did this in general for one specific project. The North Sea, I cannot tell you exactly where it was. We're not allowed to do that, but if you look good at the picture and if you look at the signage on that platform, you can probably figure it out where it was from. But basically, we had a pipe pile that had to be driven with a vibratory hammer, and we were asked to do the simulations, we were asked to do the monitoring, and then also do the analysis later on. So really involved from start to finish to figure out what would be the right thing, the right way of handling this project. Decent sized pile. So we went through the various parts that you see there, the VDP, the vibratory pile driving at the very beginning. Then we did our monitoring, the VDO, the PDA equivalent, and then your signal matching at the tail end. So all aspects were covered, and we thought we were in good shape. You see kind of the picture of the model of the various components with the vibratory hammer, where we figured out that you need to put 3 vibratory hammers in parallel, because that's most of the time how this thing works. Other than with an impact hammer, it's very simple to put vibratory hammers in parallel with a stiff frame underneath there so that they all work in parallel. And we basically take the largest vibratory hammer that somebody has and then start figuring out, do we need 1, 2, 3, 4, 5, up to 8, or even 12. And there have been projects in China where they've used 12 large vibratory hammers in parallel. The pile is then modeled. We have a soil investigation and just give you some indications of some of the dimensions. 13 feet diameter pile, 2-inch wall thickness, about 130 feet long, and you have a tip resistance with the CPT. Travis was already talking earlier about my love for CPT, so I don't give you an SPT curve, I give you a CPT curve, but at least in the US units as well, where you go with your tip resistance up to about 600 TSF. So we did a simulation for that, and we basically said, listen, the pile needs to go about 20 or 31 meters into the ground, and we make sure that we can achieve that. We were told by the operator that he would operate his hammer at 23 hertz. So we did all that good stuff there. We then also said, well, if for whatever reason something goes wrong, because I showed you earlier, we were told we had one frequency, but in reality we got a different frequency. So let's drop it again by about 10%. So get you a 21 hertz scenario. And we felt that here, this at around 10 meters, we had a major problem, a big reduction in the penetration speed, but we're still at 10 millimeters per second, so about 0.4 of an inch per second, which is still a fairly decent penetration speed. So we told them, no problems, you go ahead, we have a design that gets you to 31 meters. And that means then that we started doing the project on this whole thing. And what you see in here is a whole bunch of curves, but the most important thing is that you see it stopped all at 25 meters. And the pile had to be driven to 31 meters. And of course, that was somewhat embarrassing. Now, what I did not show out to, pointed out to you before, and I think I have it in here on one of my slides there. If not, no, not in here. We're not too concerned about this whole thing, because the client required already, or the owner in the end, that the last couple meters still had to be checked with an impact hammer. So the impact hammer was put in there. We had it on standby, and we brought it impact hammer, and we drove the pile to penetration. Everybody was still happy, except we were not, because it was embarrassing. And again, it comes back to what I said earlier. We need to have more presentations where we show embarrassing situations. Now, what happened there? Obviously, when you drive the pile into the ground, you reduce that soil resistance. And with impact driving, we know how that works. But we also know with impact driving that after you've finished your pile driving, you have soil setup. So the soil will recover somewhat. Vibratory driving, we're not using, and that's a misnomer, vibratory driving. A lot of people think that we are liquefying the soil at the bottom. That is not necessarily the case, but the vibratory movement, the vibratory action does allow the pile to penetrate, and that is, the question is then, why would there not be a soil setup? 2 comments on that. Why do I say vibratory driving is not the same as liquefaction, does not affect liquefaction? What happens with liquefaction is that the water pressure takes over, and that have no longer an effective soil pressure, and therefore you have liquefaction of the soil. Well, there have been plenty of tests done where you have completely dry soils, and nonetheless with vibratory driving you can get your pile into the ground, and therefore it cannot be liquefaction. And the fact that you have soil setup is something to keep in mind. That once you've done this whole thing, once you start doing vibratory driving, if I have vibratory setup with an impact hammer, why would I not have it, generally speaking, with a vibratory hammer? Yes, I know there are certain soil types that are an exception potentially, but generally speaking, soil setup is likely to be expected. So what did we do? With vibratory driving, you create that you have a temporary reduction of the soil resistance, and that is in the immediate vicinity of the pile. Obviously, the main thing is the shaft friction, that's completely gone. You allow the pile to penetrate, and that penetration is then also a combination of the weight of the pile and the hammer. Because that weight of the pile, especially with the larger piles, you talk about large amounts of force that allows you to get the pile to penetrate. And then, generally speaking, after termination of the driving, the soil regains most of its strength. And that's the setup. So here you see impact driving, vibratory driving side by side. And I told you that, unfortunately, at 25 meters, vibratory driving stopped. So what we did was we looked at the monitoring data. We applied signal matching, as I showed you earlier, with the matching of the amplitudes. And we applied there, just like what you would do with a impact driving, we applied there on that soil model an estimate of the static pile capacity. And we came up with about 21 meganewton. Again, units are not important. It's more the order of magnitudes of the numbers. So we were somewhat embarrassed, obviously, that something is not going right. But okay, fine. At least we know what's happening. And besides, when we did the new soil model, we got a much better indication that our soil model was initially not all that good. Therefore, we knew that you would have had the whole thing. But we also saw this as an opportunity, because now end of vibratory driving, what we normally call the EOD type signal match, call it here end of vibratory driving, EOV. But now we also had when we brought the impact hammer up and put it on the pile, which we did it about a week later, we could do a signal match as well. In a way, the restrike. And the restrike was kind of like an embarrassment, again, initially at least, because we found out that after a week, we had about 49 meganewton, or more than twice the capacity, what you had there. So substantially higher than what we had at the end of vibratory driving. But beginning of restrike. Therefore, you can take advantage of the full amount of your setup. And that's where the nice thing came, because we then said, okay, let's continue with this whole thing and let's do an end of restrike. Use the 8th or the 10th blow to figure out, because by then you have broken again your shaft friction, you get a much more normal result that you would have more comparable to your end of driving. And what you then see, your end of restrike, which normally this is an acronym that you don't see often. Most of the time we talk about beginning of restrike. Suddenly you see that your capacity went way down and was very close to what we're seeing between the outcome of what we had on the vibratory driving with what we had now with impact driving. And that was important for a couple of things. First of all, it showed that we can, especially in granular soils, in cohesive soils, in clays, it's still we don't have as much experience, because most of the time when we drive a pile in offshore, it's in sand layers in the sea. So our experience on granular soils is much stronger, but we can fairly accurately come up with a capacity prediction of the pile. It remains an estimate, because even with signal matching, when you talk about high-strength dynamic testing, it is always and remains an estimate. It's not the final value, because signal matching doesn't have a unique solution, and therefore it is subject to what the analysts think. But what you now see is that you start seeing that setup did occur, because what happened was we came up with a capacity of 21 meganewton, and yet when we were looking at the beginning of restrike, so a week later, we saw a capacity of more than double than that. And that basically confirms that with vibratory driving in lots of soils, you do have your setup, just like what you have with impact driving. You can apply the same approach, just like with impact driving, on your analysis of your data. And you can even come up with capacity figures that are fairly accurate, especially in granular soils. And we're working hard to achieve the same on cohesive soils and in clays, etc. So can a vibratory hammer be used to determine the static pile behavior? Because quite often right now we still have the situation that we insist that a vibratory pile that is load bearing, the final couple of feet is being driven impact hammer. Well, the more data we're going to get, it definitely has potential. The only thing is, this database that you see there, the red tube, is not yet as full as you have it for vibratory, for impact driving. So that's something where hopefully after you hear this presentation, we feel a lot more comfortable with this whole thing. Because remember, dynamic load testing or high-strength dynamic testing, what we've been doing with impact driving has been around for 50 years. And what we're doing, what I'm presenting right now, is really a development in the last couple of years. So what are the conclusions? Why am I so excited about vibratory hammers? Because you can get large diameter piles. If I talk about a pile, what we did in Hong Kong, a 72 footer in the ground, you cannot do that with an impact hammer. We can use those predictions to come up with the right equipment. And by now, we feel very comfortable predicting how many hammers you need. Yes, we're putting probably still a little bit too much of a safety factor in there, but that safety factor is getting smaller and smaller so that you can come up with the equipment to prevent installation problems. Provided, and I'll be very honest with you, provided you have good soil information. If you don't have good soil information, as we saw before, you may have a problem with this whole thing. And we need to really come up with the learning loop to increase the comfort zone for vibratory driving predictions and analysis. Finally, because I don't want people to get the wrong idea, I'm not saying that we should basically drop every single impact hammer and that we only should use vibratory hammer. They're complementary tools. And every method has its pros and cons. And when you talk about pile driving with an impact hammer, there are stiffer and harder soils that you can penetrate with an impact hammer that you cannot go through with a vibratory hammer. We have a huge database, so therefore we feel more comfortable. It's more calibrated on many projects. And we have extensive offshore experience. So don't get me wrong, don't take this presentation to say that Verbeek is claiming we should no longer use impact driving. But we need to recognize that there are advantages of vibratory driving. That you have low stress levels, that when it comes to pile material fatigue, not soil fatigue, but pile material fatigue, it is very friendly to use it within a vibratory hammer. You have extremely short installation times, especially in sandy soils, a few minutes, and you have a pile in the ground. Your noise levels are lower. And another important thing is that when you have the vibratory driving mode, you have it hanging in the winch. So if something goes wrong, you can basically say, okay, you vibrate your pile again, and you pull it back out again, and you start again. And that's something that's not possible with an impact hammer. So both methods have its advantages, but please, hopefully after you've seen this, you'll start to realize that we can do the same type of analysis, the same type of signal matching, or similar, with a similar outcome, signal matching on vibratory driving that you have on this whole thing. And with that, for now, Travis, back to you. We'll go from there.
I think we have some questions for you, Gerald. Thank you very much. Some super, very impressive projects. And like you said, it's not easy to, we don't often present on things that we get wrong. So thanks for the honesty. So I see that, I see these 6 to 8 hammers installing piles, or the vibratory hammers working in sequence. So one craps out. What comes next? Does it stop installing altogether? Is it slower? Is it something more complicated than just reducing the rate?
The answer is it depends, as always. If you have a pile that we have in the 82 footer, let me go back to the very beginning of this whole thing, where we had the piles kind of circled all around the perimeter.
Yeah.
Then if you have one that goes haywire, we have a problem, because then part of the pile doesn't get agitated, and it goes out of balance, and the whole thing is a problem. If, on the other hand, we have a situation like what you had in the project that I showed you in Germany, here I think it was, where you have the hammer sitting side by side on a stiff plate, there we, like in this case, where you have the pile sitting side by side on the stiff plate, there it's really no problem. If one goes out, then you lose a lot of capacity. And as long as you have, and most of the time, right now, if we say we need 3 hammers, then most of the time you can do it with 2 hammers. Most of the time we also build in a little bit of flexibility that you can use a higher frequency. Higher frequency means more force. So it does not necessarily mean that if one goes out, that you then have must have a problem. But if you put them all around the perimeter, then you do have a problem.
Okay. Well, I have a question about the frequency right now. So Someone asked, how does the variable installation frequency affect the capacity of the pile? So does higher frequency break down the soil resistance more during installation?
Yeah. If you have a higher frequency, then you have higher amplitudes in your pile movement. And if you have higher amplitudes in your pile movements, then generally speaking, you have a larger, higher penetration speed in the whole thing. And you saw that when I put the graph together there with the two frequencies, where you saw the impact of the lower frequency. Having said that, though, again, it's never as simple as one thing, because if I have a higher frequency, but at the same time, I forget where that slide is. If I have a higher frequency, but I have a higher hook load, then the hook load can offset the impact of the higher frequency.
Mm-hmm.
Yeah, so it's really a combination of everything, but all things equal, a higher frequency means that I have more space and more capacity to drive things down into to the ground.
Mm-hmm. So as I've modeled these land-based vibratory conditions, I see that they're very sensitive to the clamp weights.
Yeah.
And is that because the clamp weights or the weight of the clamps relative to the weight of the hammer, or is it something more complicated than that? I mean, does sizing a clamp on an offshore hammer by 15% in weight, does that greatly affect it like it does on land?
No, on land or offshore, you have different sizes. The weights that I showed you here in these examples of the piles and offshore piles are generally way higher. So if we're a little bit off on the weight of the clamp or the weight of the hammer, it's not that big a deal. Plus, quite often, what we have with an offshore project, you have a number of hammers working parallel, which means that I have to have a very stiff plate underneath there to make sure that the action is really shared or spread over the whole pile. That very stiff plate is generally heavy. So from that point of view, it's not that important. Where the clamps are. But the other thing that's more important than that, especially when you have these large piles, is those clamps have generally a limited amount of force that they can transmit, limited amount of weight. And if you want to be able to pull your pile back out of the ground, you need to make sure that your clamp is able to do that. So you really need to look at the clamp from two angles. One is that it spreads the force from the hammer over sufficient steel so that you don't damage your pile, but also that your clamps are able to pull the whole thing out again. But to come back to your question, onshore, a good estimate for your clamp is much more important than offshore. But obviously, you would like to have a model as accurately as possible.
Mm-hmm. Do you have any static load test comparisons to these vibratory installation conditions?
We have some,
Uh-huh.
but not as many, because what's happening for the larger piles where we're interested in offshore, you don't do static load tests. Let's face it, dynamic load testing was developed in the 1970s, at least in Europe, to start testing piles offshore with the oil and gas industry. But onshore, yes, we have some data, and generally speaking, by now, when we look at that data in granular soils, we feel very comfortable, and they match very well. Cohesive soils, a little bit more of a problem, but it could also be that in cohesive soils, the setup there is a little bit more tricky to figure out. But yeah, we have some data available to the point that there are now certain regulatory agencies that are saying that we can utilize the predictions on vibratory driving, and we don't need to drive it with an impact hammer anymore.
Okay. A participant asked, can pre-drill or relief drilling be used for early refusal situations?
Yeah, Ken?
And how will pile capacity be affected because of that pre-drill or relief drilling?
Well, obviously, what's when you have depending on what kind of pile you have, but if you pre-drill through a load-bearing layer, then you need to find something else that underneath there that has a load-bearing layer. But in and of itself, most of the time, pre-drilling is no problem. Go one step further. We did a project a couple of years ago in northern Finland, where we knew that we could not get the piles with a vibratory hammer into the ground. And what we did there, we lowered explosives onto the seabed, blasted the whole thing to create out of rock granular soils. And out of the 8 piles, and again, I'll be honest, 6 were a success, 2 were no success. With the 6 cases, we were able to get the pile with the vibratory hammer into the ground. At the same time, also honesty forced me to say that those piles were for boys, so no real vertical load on this whole thing. We're not there yet that we can say we just blast our way through and then get a capacity prediction. But most of the time what you have is that when you pre-drill through that material, you end up with still a fairly decent estimate of your shaft friction, because it's generally a fairly short distance that you pre-drill through.
Mm-hmm. So I have a question of my own, and this relates to your PDCA process. So I'm seeing a vibratory installation or modeling being specified for transmission lines, like demonstrate you can install the casing to such and such depth.
Yeah.
But that's the end of it. There's no required feedback.
Yeah.
If it doesn't work, they just tell them to get something larger anyway. So it makes you wonder why it was done in the first place. I mean, what's a suitable process to make this have some value or educate folks?
Well, why is it done to begin with? It comes back to what I said at the very end. When you have a vibratory driving, it goes a lot faster than impact driving. And that's the big advantage. So I can see that. But what we need to do as an industry is we really need to recognize that all of us, are interested in moving the industry forward. If we are only interested in doing what we've been doing for a long time, that's not going to be good, because somebody will be smart enough that they will innovate as well, and then we're going to lose out as an industry. So as a pile driving industry, we really need to start thinking, how can we be smarter? What can we learn? And I'm 62, I still learn every day. It's nonsense to say that there's nothing anymore to learn. There's an awful lot to learn. And if we want to learn, we need to get data, because only once you have data can you learn. So I think it's in the benefit for the industry, but for every single contractor as well, and even engineering firm, collect data. And then finally, and that comes back to what I said earlier, when there's a problem, and hopefully you don't have problems in every job, but when there's a problem, there's suddenly time and money to stand around and look down at the soil and try to guess what is going on there. But if I had no data, how am I going to come up with a conclusion? And the amount of money that we then waste on meetings and discussions and trial and error, that would pay for lots and lots of monitoring, where we now suddenly, then we have the data. So if you have a problem, you can do something about it. And at the same time, you start filling the database so that we can come up with better predictions.
Okay, well, I think we've used up all of our time, and there's plenty of questions that we could ask, but like I said, I think we're out of time. So thank you so much for the presentation, Gerald.
Sure, you're welcome. Been a pleasure.
And some questions were directly related to your services, so they should reach out to you directly.
Yeah.
For those services.
Yeah, what they can do is there we are. You can these are the phone numbers and the websites, and you can reach me there. Plus DFI members, you probably need, because I do plenty of stuff within DFI. You can probably know where to find me. But I'm more than happy to answer questions or talk more about this whole thing, because I feel very strong about vibratory driving. I just came back last week giving a presentation at the Offshore Technology Conference about vibratory driving. So I'm always more than happy to talk about this topic.
Thanks again, Gerald.
You're welcome.
So as Gerald showed, the vibratory database is filling up, but it's still thin relative to driven pile installation. And DFI's Driven Pile Group is trying to collect this data within the DFI webpage for the DFI Driven Pile Committee subpage. There is a link to contribute to that database if you have some vibratory installation data that you obtain. And here's your directions for your PDH certificates. They're available on your website with your when you go through this session evaluations. You can register at DFI for other webinars, and please give us feedback and suggestions. And then this webinar is presented every other month on the third Wednesday. So our next meeting will be July 19th. There are two presenters at that time. They're sort of opposite ends of the spectrum: large piles, large loads, large hammers. And then the second presenter is small hammers, small piles, or relatively small piles, and small loads. So please join us on the 19th. And thank you for the time. Thanks again, Gerald.
Thanks, Travis.